Good morning and thank you for joining this presentation about hacking the Hacktivity 2019 badge, or how to break the device and resurrect it with another soul. I am Valerio di Giampetro. I am passionate about electronics since when I was a child, and for this reason I studied electronic engineering at the university. On my daily job I am an IT infrastructure manager, managing servers but on-premise and on the cloud, managing storage, networking, databases and so on. I am also a Linux enthusiast. Almost since the beginning I installed Linux for the first time on my own PC in 1993. My personal website is Valerio, written as va.ler.io. You will find a copy of this presentation and, more important, links to everything I will talk about today. My email address is Valerio, written as v@ler.io, and my Twitter handle is Valerio. Being a nerd, I am quite proud of these addresses. I have also a YouTube channel called Make Me Hack about hardware hacking. I started this YouTube channel during the lockdown period when I had much more time to dedicate to this. What we will talk about today? Basically we'll talk about my journey in hacking the last year Hacktivity badge. This has a lot to do with hacking, maybe a bit less to do with the security, also if the two items are very strictly related. I will introduce the Hacktivity 2019 badge. I explain how I bricked the badge, how I reverse engineered the PCB to reconstruct the most important part of the schematics, then how I used the Arduino IDE to reprogram the main processor, the ESP32 processor, and how I reflashed the coprocessor, that it is an ARM-based SUMD21. The Hacktivity 2019 badge was a nice, cool gadget that was distributed to the attendants at the last year physical conference in Budapest. It has a lot of interesting features because it runs MicroPython. It has connectivity, but USB, Wi-Fi and infrared connectivity. It has an app store where you can download applications written in MicroPython and upload your own applications. Has 6 nice touch buttons, a small monochrome but nice LCD screen of 128 for 64 bits, has 6 RGB LEDs, an infrared transmitter and receiver, has also a buzzer, and can be powered by USB or by battery. It is been designed to be hacked, but there are no detailed information on hardware and firmware about this device. It is a pretty powerful device. At its core there is an ESP32 Vroom32 module that has a 32-bit dual-core extensor CPU, has 4 MB of flash memory, 520 KB of static RAM, has Wi-Fi and Bluetooth connectivity, has a lot of digital, analog and pulse width modulated I/O pins, support touch sensors, can have multiple serial interface implementing multiple protocols like UART, SPI, I2C and so on. Has also an ultra-low power mode. The coprocessor is also quite powerful. The coprocessor is needed. The main purpose of the coprocessor is to talk the USB interface, because the ESP32 doesn't support the USB interface. The coprocessor is an Atmel SUMD21G16B that has a powerful ARM Cortex M0 CPU, has a small amount of flash memory, only 64 KB, and a small amount of static RAM, only 8 KB. Has the serial wire debug interface, that interface is similar to the JTAG interface, that allows to reprogram this chip and to also do in-circuit debugging, being able to execute step-by-step a program directly on the hardware. Supports the USB interface, has multiple serial interface implementing various protocols, has digital, analog and pulse width modulated input-output pins, support touch sensors. How I break the device? After playing a bit with the MicroPython on this on this board, I tried to use the Arduino IDE, wrongly assuming that this board was similar to some board used for Arduino. So I connected my board to my Arduino PC. The badge was recognized as another Adafruit Playground Express board. I suppose that this was correct, so I loaded the simple blink sketch to blink a LED. The load was successful, but then the device was bricked. Bricked means the device was dead, and the USB was no more recognized by the PC. Plugging or unplugging the USB didn't do any effect on the PC. So after this, I asked myself why this has been wrongly identified as Adafruit Playground Express, because this board is the one that you see on the slide, is a processor that is almost identical to our processor. It's an Atmel SUMD21G18A, our instead is 16A. It is basically identical to our processor. The only difference is that the Playground Express has 4 times more flash and 4 times more static RAM. Probably our device, our badge, has been implemented in some way, copying the Adafruit Playground Express, and so it was wrongly recognized. But because the flash and static RAM are different, the sketch that was loaded probably simply bricked the device, and the device became unuseful. So the first step was, okay, I have to understand what's going on the board, how the chips are connected, and what signals are available on the interface. So the first step was to solder pin headers on the board that ships without pin headers. Then try to find the pin headers connections. Some connections were quite easy to find because the board is a 2 layers board, and you are able to see the traces on the board, so many of them are quite easy to follow. Obviously, you can always confirm the connection using a multimeter. I also searched on the internet, and I was able to find these 2 images that are images of the top and the bottom of the printed circuit, also without components, so it's quite easy to follow PCB traces. I also searched on the internet and found, I wasn't able to find the schematic of this badge, but I found a schematic of a different badge, the Disobey 2019 badge, that was designed by the same team. So probably this schematic can be similar to our schematic. I used the GIMP, that is the open source, I would say something similar to Photoshop but open source, to follow the image with the PCB layout. But during this activity I discovered that what I found on internet, the image of the top and bottom of the PCB, was not identical to our finished product. For example, if you see on the image I downloaded from internet, I have a connector with 4 pins. On the same position, in the real board, I have a connector with 17 pins. So probably these images available on internet are related to some prototype of our board, and then our board was later modified. So what I found on these 2 images must be checked with a multimeter. So I followed the traces using GIMP, putting each image on a separate layer and then alternating the visibility of the 2 layers, so it was quite easy to follow each PCB trace and reconstruct the schematic. But I also used the similar project as a hint, what I found relating to the Disobey 2019 badge, the schematic. I said, okay, so probably connections are the same. And also I used as a hint the datasheet, because if you have on the datasheet, for example, a reset pin, probably that reset pin goes to a push button to reset the board. Or if you found pins that are used to connect the USB interface, probably these 2 pins will go to the USB interfaces. So taking this information that are not strictly related to our board, but from similar boards or datasheet and so on, I confirmed the connection with the multimeter. Anyway, this information was useful to speed up the reconstructing of the schematic. So I was able to identify each connector, which signals we have on each connector, and I found interesting things. For example, the connector J9 is the I2C bus. I2C bus is a serial bus often used in electronic circuits. It allows a master to talk to multiple slaves. Each slave has an address. In this way, we can see what's going on the board, monitoring these I2C pins. The J10 connector exposes a lot of pins of the ESP32 main processor, and this can be used to attach sensors, switches, additional peripherals to our badge. The J11 connector is a very interesting connector because it exposes the serial wired debug interface of the SAMD21 coprocessor, that is an ARM-based coprocessor. The serial wired debug interface is very similar to the JTAG interface because it allows to reprogram the device and to use this interface as a debugging support to do in-circuit debugging. Here we have the two pins of this interface that are the data input-output at the clock, plus ground VCC and the reset pin of the coprocessor. The pin header J12 exposes other pins of the ESP32 main processor. One of these pins is quite interesting for our purpose because it's the so-called bootloader pin. This means that if we reset the ESP32 and keep low this pin during a reset, the ESP32 will enter the bootloader mode and will allow to load a firmware through the serial interface. The J13 connector is the serial interface of the ESP32. We have the TX, RX and ground connection. On the bottom of the board we have two switches. We don't have the actual switches, only the pad. The switches we can put by ourselves, but anyway we have two switches. One is to reset the coprocessor, the SAMD21 ARM coprocessor, and the other one is to put in bootloader mode the SAMD21 coprocessor. Obviously, to put in bootloader mode you have to reset the coprocessor, keeping low this pin, but to put in bootloader mode you have a bootloader functioning of the coprocessor. I bricked the device, so this was no more functioning because I destroyed also the bootloader. And I also found the main connections between main processor, coprocessor and the display. The most important connection is that the coprocessor uses the UART serial interface to talk to the ESP32 and act as a bridge between the USB interface and the ESP32. Then we have the I2C interface, the serial interface that connects the main processor, the ESP32, that is the master in this network. The SAMD21 coprocessor is one slave and the display is the other slave. And then the SAMD21 coprocessor has the possibility to reset the main processor, driving the EN pin. EN pin is enabled, is the reset pin, and also being able to drive the bootloader pin. So the coprocessor can reset the main processor and can also put the main processor in bootloader mode to load the firmware inside the ESP32. The SAMD21 coprocessor not only drives the USB interface, but also all the touch buttons that are available on the board and all the RGB LEDs available on the board are attached to the coprocessor. So this means that the coprocessor will read the touch buttons and will switch on and switch off the LED. And the main processor will ask to the coprocessor to do these operations on its behalf using the I2C serial bus. My idea was to be able to use the ESP32 using the Arduino IDE. So first step was, okay, let me check if I can use the ESP32 directly with the Arduino IDE interface. And because we have exposed the serial interface on the board, I could attach a TTL serial adapter to connect to this serial interface and to a PC running Arduino. Then I can use a jumper to put low the bootloader mode during reset to have the ESP32 enter the bootloader mode to load the firmware. Then I can reset the board, unplugging and replugging the power, that is the USB connector. And in this way, the ESP32 will enter bootloader mode, and I will be able, through the Arduino IDE, to load a simple sketch. Then I can remove the jumper, reset again the board, unplugging and replugging the power, the USB interface, and in this way my sketch will run. Now a simple demo of this approach. So here we have our activity badge. Here there is the serial connection with a TTL serial adapter. Here there is the bootloader switch with the jumper that activate the bootloader switch, because one is ground and the other pin is the bootloader switch. And here I connected a LED connected to the GPIO 21, it is the red cable, and to ground, it is the green cable. Now, powering up the device, the ESP32 should enter the bootloader mode. After we power up the device, we also attach the USB TTL serial adapter to our PC. We can check using a PUTTY terminal emulator. We can check that it has really entered the bootloader mode. To be sure, we power down and power up again, and we can see that on the serial console we receive the message waiting for download. This means that ESP32 is ready to download a new sketch. So we close the PUTTY and download this simple sketch. This sketch, you can see, basically print a LED on message on the serial console, light the LED, delay half a second, another message to the serial console with the LED off, and then switch the LED off. Wait half a second again, and the cycle repeat. You can see that now it is loading, Arduino IDE is loading the sketch. At the end it says hard resetting via RTS pin, but the RTS pin is not connected, so this means that Arduino IDE is not able to reset the ESP32. So we have to reset manually. First of all, we disconnect the jumper to select the bootloader, so next time it will boot normally. We disconnect also the USB cable, because otherwise there is some possibility that the power goes through the USB cable to the board and it will not reset correctly. We power down, power up again, and we can see that the sketch has been successfully loaded because the LED is blinking half a second on, half a second off. We can also see that something is printed on the serial console as per our sketch. We execute again the terminal emulator, select the COM9 interface, open, and we can see that it is printing LED on, LED off as in the per our sketch. So basically we have successfully loaded the sketch on and the ESP32 using the Arduino IDE. One important thing to note is that the coprocessor was bricked. Bricked means that basically nothing was running, or casual instructions were running, and by default when the coprocessor, this ARM chip, power on, by default every I/O pin are automatically configured as input pin. So this coprocessor was not driving the TX pin. For this reason I was able to program the ESP32 through the interface, the J13 connector, because otherwise the SUMD21 would drive the TX pin, it will win because we'll go directly to the ESP32 pin. Instead, on the interface, we have a serial resistor. If you have a functioning badge, this example will not function. To have it function, you have or to brick the device, or you have to put the SUMD21 coprocessor in bootloader mode, because in bootloader mode, all input-output pins are automatically configured as input pins. Once I was successfully to use the Arduino IDE, I wanted also to refresh the SUMD21 ARM coprocessor. Why? The first reason is that I want to use the available USB interface on the board to program the ESP32 with the Arduino IDE without using additional circuitry like a TTL serial adapter. To do so, the SUMD21 coprocessor I have to read from the USB serial interface and have to write to the ESP32 serial interface and vice versa, making a serial bridge. I also want to switch on and switch off the LEDs that are attached to the SUMD21, and I also want to use the touch buttons that are attached to the SUMD21. So for this reason, I want to rewrite a simple firmware on this coprocessor and interface it with the ESP32. To do so, to refresh, at least I need a hardware to refresh, some probe to refresh. On the badge we have the serial wire debug interface that can be used to refresh the device, and we can use, but we have to use a simple interface. We can use a probe. One of the probe that I used, that I strongly recommend to use, is the Seger J-Link Edu Mini. That is a very small probe, but very good probe that is very well supported by open source tools and also by proprietary tools like Atmel Studio. It is quite cheap. It is the Edu versions. Edu version means that you can use for hobby or for educational purposes, but you cannot use it for professional use to make money with this. To use for professional use, you have to use a normal J-Link probe that will cost a few $100s, but has more or less the same capabilities of this probe. There are also some other alternatives. One very popular alternative is a breakout board based on the FT2232 chip. That is a chip that is on one side a USB interface, and on the other side it has two serial interfaces where you can program multiple protocols, including JTAG, SWD, and so on. But this interface you have to use with an open source software like OpenOCD, and it's not integrated in main commercial software like Atmel Studio. A bit more complicated to use, but a good alternatives. Some other alternatives were popular in the past, but today are not more so used, like Bus Blaster, based on the same chip, but more expensive, or Bus Pirate, that is very versatile, but is also slower, and anyway, it's also more expensive. Once we know how to refresh the firmware, we have to develop the simple firmware that does what we want. To develop the firmware, the natural choice is to use Atmel Studio. That is the suite of tools, the IDE integrated tools to develop firmware for Atmel chips. It is freely available, so you can download and install, but it has some drawbacks. First of all, is Windows only. Usually I am forced to use Windows during my daily job, but outside of my daily job I try to never use Windows, so this was not the best option for me, but was only options. It is overbloated because it took about half an hour to install on my old Windows PC. The Atmel Studio itself is more than 4 GB in size. More you have Microsoft Visual Studio, this is another 1.5 GB, and it installed a lot of additional software like .NET frameworks and so on. It is totally graphical user interface based. Also, to do simple things like assigning a label to a pin, you have to use the graphical user interface. It is a really overloaded Atmel software framework, so if you do a simple project like blinking a LED, you use the GUI interface to generate the template for your project. And the template for a simple project like blinking a LED is literally hundreds of files, so really bloated environment. The graphical user interface is very easy to use, but allows you to create illegal configuration. So you create some configuration, compile everything, put the firmware on your chip, but the firmware will not run, will not do anything, because maybe you have wrongly configured a clock signal. And the clock configuration is quite complex, because you try to use the GUI without reading the datasheet, and it's very easy to make some illegal configurations, because it's not easy to understand what you can do and what you cannot do. But in any way, Atmel Studio has also some nice features. For example, Visual Studio is a good and pleasant graphical user interface. It is very well integrated with the J-Link probe, so it's very easy to flash the device from inside the IDE. You click a menu and are able to program a device with the firmware you have just compiled. And it is also very easy to debug your program, executing it with a debugger, executing it step by step on the real hardware. So I wrote a simple hello world program in the hardware embedded space. Hello world means lighting some LEDs. In this case, I wrote a simple hello world program that basically alternates the colors red, green and blue on the LEDs, and then toggle each one of the 6 LEDs on the board. I programmed this with Atmel Studio, and I wrote this firmware on the SAMD21 coprocessor. Maybe because we light a lot of LEDs, maybe it's not an hello world program, a Merry Christmas with some in advance, but anyway, this is a small demo of this program. So here we have our Hacktivity badge 209 This is the Segger J-Link Mini Edu probe. This is the simple breakout board to convert this small cable to these bigger cables, and these cables are attached to the SWD interface of the SAMD21 ARM processor. We can now program this processor using Atmel Studio. Here it is a very simple program that basically set the LED colors to blue the first time, to green the second time, and to red the third time, and then it repeat again this cycle, and switch on and off each one of the LEDs, toggle the level of each one of the 6 LEDs. So we can build this program with build solution. The program has been built, and then thanks to the integration between the Atmel IDE and the J-Link Edu Mini, we can go directly to the device programming menu. We have selected the correct device. We click to apply. We can read from the device, and then we can go to memories to program the device. And we click program, and then the probe will program the device, reset the device, and as you can see, we have blinking LEDs. The color of the LEDs switch between green, red and blue, and each single LED toggle its status in each cycle. So we have built our Hello World, or if you prefer, our Merry Christmas program in hardware. But after spending a few weeks with Atmel Studio, I tried to write a simple program to read from the USB serial interface and write to the ESP32 serial interface, making a USB bridged. But I found very difficult to find some examples on the internet and to mix and merge these examples. So at the end, I understood that I should write by myself and from scratch. It is a simple program to read from USB interface and write to the ESP32 serial interface. But I found that I didn't succeed in writing this simple program. It seemed impossible to write this program without reading the 1000 plus datasheet pages of the SUMD21 or without reading the 500 pages plus of the Atmel Studio manual. So basically the Atmel Studio Way was the opposite of the Arduino Way. And so I started searching on the internet on how to bring the our SUMD21 chip inside the Arduino IDE, knowing that similar chips like the Adafruit Playground Express, that a similar chip but with more flash and more static RAM, are already bringed inside the Arduino IDE, because Arduino IDE is much easier, because the philosophy of Arduino IDE, as was written by Massimo Banzi, one of the co-authors of the Arduino, is that there is the concept that rewriting from learning how to write things from scratch is a waste of energy. What you want to do is to reuse what other people have already done, and being able to very fast make some prototypes, and then if needed you investigate more. And I love the Arduino Way because it would allows an hobbyist to very fast start playing with hardware and later investigate more if needed. I was quite lucky, because not only I found that someone on the internet has already ported our coprocessor inside the Arduino IDE, and I should found this before trying to do things with Atmel Studio, but this was brought inside the Arduino IDE by the same folk, the same people that designed our badge. And what I found on the internet was a project for another badge, the Disobey 2019 badge, that is very similar to our badge and was designed by the same people. And I also found a similar repository where I found the schematics of the Disobey 2019 badge that helped me to reconstruct the schematic of our badge. And in the what I tried to do without success with Atmel Studio, spending weeks of hobby time inside the Arduino IDE, is very easy. So in the Arduino IDE, the USB serial to ESP32 serial bridge is done with only 10 lines of code. You read from one serial interface with a simple call and write to the other serial interface with another call, and vice versa. So I rewrote the bootloader on my SUMD21 coprocessor. The bootloader was available on this repository, and I compiled with the Arduino IDE the firmware available in this repository, loaded inside SUMD21 using the procedure that is available on this repository using a diffutil. And so I should have everything ready to use with Arduino IDE. So I tried to load a sketch into the ESP32 using the Arduino IDE, but with my surprise, I found I cannot do. I found an error during the loading of the sketch. Basically, the problem was that the serial bridge was not fast enough. The serial bridge was dropping bytes during the programming phase. The problem is that Arduino IDE is fantastic, it's very easy to use, very simple, but it hides complexity and sometimes can generate code that is quite inefficient. So in this case, it wasn't able to read and write on two different serial interfaces without dropping bytes. Basically, to solve the issue, what I did was to increase the TX and RX serial buffer from the 64 bytes to 512 bytes. This value probably was so low because our coprocessor has a very small amount of static RAM, so saving each byte was important. In this way, I add more room to prevent dropping of bytes. And another modification was that I rewrote the serial bridge to be non-blocking. This means being sure to have already a byte available in Rx buffer before reading from the serial interface, and being sure to have 3 bytes available on TX buffer before writing a byte on the serial interface. In this way, each call will return immediately without waiting for the actual byte to be received or to be sent. After these new modifications, our serial interface was working as in this simple demo. Now I will show you that we are able to upload our sketch for the ESP32 processor, and that our sketch will be able to talk to the SAMD21 coprocessor and will be able to switch on and off few LEDs, and also to read the status of the touch buttons that are attached to the coprocessor. We can see that we have selected as our board the ESP32 development module. Basically, we will drive our ESP32 directly, and as port we have COM10, that it is our Disobey Badge 2019 port. So we can now press this button. This will compile our sketch and will upload this sketch. You can see that it is driving the COM port and that it is uploading our sketch. Now uploading is finished and it started to power on some LEDs, but there is too light, so you can see I will lower the light. Just 1 second. Now it's easier to see the LEDs lighting, and we can also see that we can read the touch buttons. If I press the up button, the backlight of the display goes on. So I can press off. If I press the down button, I select the LED, the red color for LEDs. This select the blue color, and this one select the green color. This left button will keep on all the LEDs. I can combine multiple buttons, so we have all LEDs on and red or blue and so on. I can also drive the buzzer clicking the right button. As you can see, we have successfully loaded the sketch on our board, and everything is going well. This is very nice Arduino. Now it is very nice Arduino development board. We have removed the MicroPython and a quite powerful Arduino development board with a nice display, LEDs on the board, touch buttons, and also infrared and a lot of available pins. In conclusion, I was successful in bringing the Arduino IDE, using the Arduino IDE to program the ESP32 on the badge. And basically in this way, the Hacktivity 2019 badge is a nice Arduino IDE based development board, very nice development board with touch buttons, LEDs, a nice display, infrared and so on. A very nice development board. There is something still to do yet that I am doing, and I will publish on my website when done, to modify an existing library to drive the display, because the existing library is able to drive the display, but only using the SPI interface and not the I2C interface. And as in every project, I learned something, or better, I reinforced what I already knew. One of the first principles is that never to get stuck. If you find a stumbling block on your road, you have to find a side way. You don't have to insist to go forward in the road that is blocked. In this way, I should have spent less time with Atmel Studio in trying to bring this coprocessor inside the Arduino IDE before insisting with the Atmel Studio. And another very important information that is always useful in every reverse engineering project is to use also partial information, like information from a similar product made by the same company, because very often information from similar products can be very useful to speed up your reverse engineering process. You have to check and verify that everything you find on a similar product will apply to your device, but anyway will help a lot in speeding the reverse engineering process. Thank you for your time. I am now available on Zoom for your question.